Welcome everyone. Today we have Joey Iverson from Iowa State University, and he's going to tell us about equiangular lines over finite fields.
Thanks, and thanks to all the organizers for putting this together, and I also want to thank the other participants for what's been, at least so far, an interesting workshop. It's been nice getting to know people. I know some of you, but more of you. This is kind of the first time. Also, I need to apologize. I'm getting over a cold. My family, we isolated for a whole year and like barely went outside, and we got COVID shots and kind of peeked our head back into the wide world and immediately got colds. So I guess that's cosmic justice or something. So anyway, that's what's happening. I want to talk today about equiangular lines over finite fields. This is joint work with these folks, with Gary Greaves from Singapore, John Jasper at South Dakota State, and Dustin Mixon at Ohio State. I should also mention that this came out of a workshop at Oberwolfach, and I got up early to get on the plane to Germany, and my brain was firing all kinds of random signals. And then one of the random things that signaled at me was, "Hey, Joey, do you think Sounder's conjecture holds over finite fields?" And I don't know, brain. And then I asked some of my friends, and well, when we got to Germany, then we were talking about it. And this is kind of what came out of that. So this is sort of a simulation of a problem that people care more about. And so the first I'm going to tell you about this problem that's more classical, just for context, about real and complex equiangular lines. And then we'll talk about equiangular lines in finite orthogonal geometry, which is a little bit like the real case. And then we'll talk about unitary geometry, which is a little bit more like the complex case. So this is the line packing problem. And you can imagine so we fix a dimension D and we fix a number of lines N. And your job is to arrange these lines. And when I say lines, I mean lines through the origin or one-dimensional subspaces. Your job is to arrange these lines in such a way that you have no sharp angles. So I used to say that this is like putting kids in the back seat of a car, that no two kids want to be near each other. But now, okay, now maybe it's a social distancing problem, that you're, maybe you work for a university that's like subject to political whims, and suddenly you have to teach online in person during a pandemic, and you're trying to arrange the seats so that no two students are near each other. And maybe your first shot is like this, and oh no, red and blue are too near each other, and you rearrange, and eventually you come up with something like this, and you think this is probably as good as it can be. Okay, so that's the geometric view, but I'd like to attack it with linear algebra. So I think this way instead, that instead of lines, I'm going to have vectors. So for each line, I choose a unit norm representative, and well, for us, normally we'll stick it into columns of a matrix like this. And now, instead of talking about angles, I talk about inner products, right? Because as we all know, in this picture over here, cosine of theta is the absolute value of the inner product between those two vectors. Okay, so I'm trying to avoid sharp angles, and a sharp angle has a big cosine, right? Like 0, cosine of 0 is 1, whereas cosine of pi over 2 is 0. So I'm trying to avoid sharp angles. I'm trying to avoid big cosines. And as a measure of how bad my packing is, the sharpest angle has the biggest cosine, okay? So here, this is the biggest cosine, and I would like that to be small. So my job is to minimize this biggest cosine. This biggest cosine is called the coherence, and I would like to minimize coherence. Okay, this is the line packing problem. So I don't want to say too much about the applications, but just to give you a hint of why someone would care about this, maybe you find yourself in a situation where you need to uniquely solve an underdetermined system, which sounds crazy, but hold on a second. So this actually arose because they were trying to speed up MRI machines. They didn't want to keep kids in MRI machines for very long because they have to stop sick kids in MRI machines because they have to stop respiration. And they wanted to make it go faster. If they make it go faster, they're taking fewer measurements, and that gives you fewer equations over here. And if you keep speeding up, eventually you have fewer equations than unknowns. And how are you going to actually find the picture of the MRI? Okay, and you may be saying, well, that's crazy. You you can't do it. Sorry, the short fat matrix has a kernel. But if you knew something else, you could do it. So if you could massage so that your vector has a lot of zero entries, then you can do it. So this is called compressed sensing. Essentially, phi x equals y has a unique sparse solution, that is with a lot of zeros, if you know a couple of things. So if you know that x has a lot of zero entries, and if you know that the columns of phi are somehow very different, and I'm not telling you what it means, just put it in quotes, then you can do this. And more importantly, you can find this through a linear program, not even semi-definite programming, but through a linear program. You can find it quickly if you can meet these conditions. So I didn't tell you what very different means, but I'll tell you a moral theorem, which is that if you look at the columns of phi and they span lines with wide angles in between them, then this can serve as a guarantee of being very different. And if your coherence is better, then you can get away with having fewer zero entries in that x, and you can take fewer measurements. Also, is sort of a different view. Okay, so let's suppose you arrange the kids in the backseat of your car, or you arrange the desks in your classroom, and it looks pretty good, but you want to know if it's optimal. So you'd like a certificate of optimality. So there's a classical bound called the Welch bound, and it says if you've got n unit vectors like this, spanning, they span either RD or CD, then their coherence satisfies this bound, and the exact number is less important here than that there is a bound, okay? And what I really care about is the certificate of equality. So I hit this bound if and only if I'm what's called an equiangular tight frame. Equiangular means that all the angles are the same. All of the different inner products have the same absolute value. And tight frame means that phi star is a constant multiple of the identity. So what's important is these are algebraic conditions. And when I spot these algebraic conditions, that is a certificate of optimality. And when I start playing with finite fields, what I'm going to do is I'm going to simulate these algebraic conditions. Okay, and here's proof is kind of a strong word. It's more of a sketch. But so I look at the Frobenius distance squared between phi star and n over d times the identity. So this n over d, it turns out that would have to be the constant. You can prove this with a trace. And if you open this up, you open up the inner product squared, the Frobenius inner product squared, and you fiddle around with it a little bit, and eventually you find it's exactly equal to this. Okay, well, here I have an upper bound for all of these entries, at least the ones on the off diagonal, the ones where I is not equal to j. So all of those ones where I is not equal to j, and there are n squared minus n of those, they're less than or equal to mu squared. There are another n where I equals j, but those I know that the inner product is exactly 1 because these are unit vectors, and then I'm subtracting this. Okay, so you look at this whole inequality and you rearrange, and then you get that bound from mu squared. But importantly, I know when I hit it dead on, right? Because there are two places where I actually had a chance for inequality. One was here, and that I will hit if phi star equals n over d times the identity. And the second was here, and that I will hit if I didn't lose anything when I made that upper bound, if all of these things are exactly equal to mu squared. Okay, so that's the proof of the Welch bound. So it's called the Welch bound, and you see this is from 1974, but maybe it shouldn't be called that. Maybe it should be called the Lemons and Seidel bound or something like that. I think in the combinatorics community, this is better known as the relative bound. And here we have a slightly different view. Before I had fixed d and n, and I was allowing all of my angles to vary. But on this slide, you see, I'm going to insist I'm equiangular, and I know what mu is. I'll fix d, and I'll allow n to vary. And I ask myself how many equiangular lines with inner product mu I could get. So if you rearrange what I had on the previous slide, then you find this. This is called the relative bound. If mu squared is less than 1 over d, and I'm equiangular with angle mu, then n can be no more than this. And equality holds again if and only if phi is an equiangular type frame. Okay, so that's a relative bound. There's also an absolute bound. This is due to Gerson. This is Michael Gerson was he helps develop like quadraphonic sound. He was into signal processing and things like that. So this one does not depend on the angle. Here I just have some I have some equiangular lines, say n of them, this is an important number, and unit vectors in RD or CD, and it's equiangular, then the most you could possibly have is, in the real case, you can have d plus 1 choose 2, and well, okay, you can have no more than d plus 1 choose 2. In the complex case, you can have no more than d squared. And here, if equality holds, then I know that phi is an equiangular type frame. And the proof here, okay, what I have here is really, John Yard gave us the same proof yesterday. So I look at the outer products. These are the rank 1 projections onto those lines. And I look at their inner product in the Frobenius inner product. Okay? And I look at the whole Gram matrix of those inner products. So this Frobenius inner product, if you open it up as a trace and you cycle that trace, then what you'll find is it's exactly equal to the absolute value squared of the inner product between those vectors. Okay, so now I look at this whole Gram matrix and I see, these things are constant off the diagonal, right? They're equal to mu off the diagonal. So I have like mu times j, and then on the diagonal, they're all equal to 1. So this whole Gram matrix is just mu times j plus 1 minus mu times the identity. And the key thing is that this, I didn't say that this is invertible. Okay, so if you have, okay, in a real complex vector space, if your Gram matrix is invertible, then your things have to be linearly independent. So these things have to be linearly independent, and they're all self-adjoint. So I've got these linearly independent vectors in a real vector space of self-adjoint matrices, so I can have no more than the dimension of that space. And that dimension of that space is exactly what I wrote up here. In the real case, it's d plus 1 choose 2. In the complex case, it's d squared. So that's just the proof of the bound. Okay, so here, these are the major open problems that we're really interested in, finally, in thinking about. So in terms of the relative bound, I'd like to know for which d and n is there a real d by n ETF to hit the relative bound or a complex. And the real and complex cases here are very different. In the real case, it turns out that real ETFs are equivalent to strongly regular graphs where k equals 2 mu. And so there are all kinds of integrality constraints about strongly regular graphs. We know many necessary conditions. Here, the smallest open case is whether or not there exists a 33 by 66 real ETF. And the complex case is much harder. So we know many examples. We know almost nothing more than what I just told you about non-existence. Well, okay, slightly more, but okay, so that's relative bound. The real absolute bound, I want to know for which d can I hit that Gerson bound? For which d does there exist a real d by d plus 1 choose 2 ETF? And existence so far is known only for 4 dimensions, 2, 3, 7, 23. There are many necessary conditions are known. We know that either d is in that list or d plus 2 is necessarily an odd square. So there's more than that I didn't say, but just to give a sense of how much more we know about this. And the next open case would be whether you could hit the Gerson bound when d is 79. Okay, another major open problem, which John Yard talked about a lot yesterday, is called Zauner's conjecture. And here, it's not a problem. The conjecture is that you always hit the Gerson bound, that in complex space, you always have a d by d squared ETF. And here, this is a lot of what John Yard talked about yesterday. So there's numerical evidence for d less than or equal to 151. And it's not like we couldn't find it in 152. It's just that eventually your computer is taking too long and you go, come on, it's true. It's known for only finitely dimensions d. Here, okay, at some point I made a slide and I think this is the case up to 24. I don't know what the current state is. People are always adding one more, but I'm quite sure that it's only known for finitely many dimensions. There is a cash prize. Currently, you'd get 2,021 euro if you can prove that this holds in infinitely many dimensions. It's a hard problem, and it seems related to number theory. It seems related to the Stark conjectures and to Hilbert's 12th problem. This is a hard problem.
Joey, you have a question in the chat.
Oh, I'm sorry. I don't have the. Can you read it to me, please?
Oh, sure. So it's a 33 by 66 solved by Gritsenko's new graph, strongly regular graph with parameters 65, 32, 15, and 16.
Oh.
That's a brand new graph, Joey. I don't know if you heard about it.
No, I had not. is k equal to 2 mu? I'm sorry, I don't have the chat in front of me.
Yes, yeah. Mu is 16 and k is 32.
Ah, excellent. I have to change a thing. I don't know what this is. So yeah, that'll do it. Wow, cool. Thank you. I did not know that. Yeah, so that will, well, okay, I guess you'd have to look at, okay. The one more thing to check is just what the multiplicity of the eigenvalues are, but
Yeah, it comes from a two graph, so it's equiangular lines.
Oh, okay. Yeah, then that's it for sure. Yes. Okay. Thank you. Thank you for telling me. I did not know that. Okay. So smallest open case is even bigger than that now, apparently. Okay. Thank you. Okay. So what we're going to do is we're going to think about finite versions of these problems. So we'll think about finite orthogonal geometry, which is a little like finite version of real space. And we'll talk about unitary geometry, which is a little like finite complex space. So what's coming in the rest of this talk, I'll give you some basic definitions and results. I'll tell you about interactions with the real and complex cases and with some other problems you hopefully know and care about in algebraic combinatorics. And I'm going to tell you something very interesting, which is that Gerson's bound is saturated infinitely often in infinitely many dimensions for both the orthogonal and the unitary geometries. Okay, so in this section, when I'm talking about orthogonal geometry, I'm always going to have an odd characteristic. I'm always going to have an odd prime power. When I do unitary geometry, I'd be cool with even, but here, just even characteristic orthogonal geometry is a different animal, and I'm not playing with that animal. So in orthogonal geometry, you can think it is identical to a non-degenerate bilinear form on FQ to the D. And this just means, so it's, sorry, I should have said symmetric. Okay, so it's symmetric and it's linear in the second spot, then by symmetry also linear in the first spot, and non-degenerate. So this is, I'm annoyed at how I phrase this. So if you have a non-zero x, then I look at x against other things. That's a linear mapping. It's not the zero mapping. So any non-zero x, there has to exist a non-zero y that I put here, and I get something non-zero. This is non-degeneracy. So examples would be just doing the dot product, and that's one that I like to think about. Another thing is if you have any symmetric invertible matrix, then you can do sort of dot product with M in the middle. Okay, and actually every example has to take that form, where if you just take the standard basis E1 through En, and then you look at their inner products, that will give you what your M is, and okay, they all have to look like this. So a funny thing happens in finite fields. There are always two kinds of orthogonal geometry. There's only one kind of dot product in the reals, but there are two kinds in orthogonal geometry. So let me just briefly explain this. So I'm always going to I'll write FQ cross for the multiplicative group of units in this finite field. And then I'm going to write cross 2 for the subgroup of quadratic residues. So these are non-zero squares. So just indulge me for a moment if I wanted to change my basis. So suppose I already have this M to write my dot product like that, or my inner product like this. And now I change basis with some B. So now when I do in my new basis like this, you see it's like I have B transpose MB. Okay, but there's an invariant, because if I look at the determinant of my new gram matrix, I get determinant of B squared times the old one. And so you see I'm multiplied by a square. I'm in the same coset of the quadratic residues. And this tells me that if this coset is an invariant of the geometry. Okay, so it's kind of annoying. And it turns out that up to a linear symmetry, there are exactly two kinds of geometry that can happen. There's a square type where your gram matrix is a square. So that would be, for instance, here, the dot product, where M is equal to I. But there's a second one, the non-square type, where the determinant is not quadratic residue. So it's an annoying thing we have to think of. Okay, so now I want to tell you about frame theory. So it's a little funny because I know that many of you do not know about frame theory in the real and complex case. So Your first definition is this kind of thing I invented with my co-authors. Okay, so I fix a geometry, an orthogonal geometry, and I have some scalars, A, B, and C. I have a sequence phi 1 to phi n. So I'll call it a frame if it's just a spanning set. And in finite dimensional real and complex cases, that's exactly it. So frame, if you never leave finite dimensions and you hear the word frame, you can just think this just means a spanning set. But more often than not, we care about what's called a tight frame. So I have some more condition. So here, I'll have a scalar C and I'll call it a C tight frame. If I want two things, and I want to highlight this, I insist that it spans, first of all, that it is a frame. And secondly, I want this condition to hold. And this, you should look and think this is kind of like being an orthonormal basis, right? So I have a spanning set, but I know one way to find the coefficients to expand. It's just doing the inner product. Except I'll have this C that I have to account for. And I have to warn you that in finite fields, C could be 0. And that's why I insist that it spans. And then I'll talk about an equiangular system if these two algebraic conditions hold. So the first is sort of like a norm squared is always equal to A. The second here, I'm trying to simulate absolute value of inner product. So I just square it. And in the orthogonal case, that will be enough. So I have these parameters A and B. So A, you think this is like the norm squared, and B, you think this is like the inner product squared. Okay, and finally, if I had both of these things at the same time, I'll call it an ABC equiangular type frame. If it's equiangular, an equiangular system, AB equiangular system, and also simultaneously a C type frame. So I want to find them. Okay. All right, so this is meant to sort of simulate finite dimensional real space. But I want to tell you there are some differences. So here I'm going to just illustrate some differences. Here I'm going to have p equals 3 and I have the dot product. So the first is the existence of isotropy, that non-zero vectors can have, their norm can be 0. And you can see this just by doing all one's vector in 3-dimensional space. So this is quite important in finite geometry. This is what makes a lot of things interesting, but it's very different from the real case. The second thing, this could not happen in the real case, that tight frames can have constant 0. And here's just a quick example, just in one dimension. Here I have sort of 3 vectors. They're all just the scalar 1. But here phi transpose is 0. So that's kind of gnarly. And those are structural features. The third is sort of a procedural feature. It's how we do math. And as a harmonic analyst, this terrifies me. The spectral theorem fails spectacularly over finite fields. So here's an example. I just do 3 by 3 all ones. Its square is 0. So its minimal polynomial is just t squared, right? And so its only eigenvalue is 0. It's nilpotent. Well, it can't be diagonalizable at all, much less, orthogonally diagonalizable. It can't be diagonalizable at all because it would have to be similar to the 0 matrix, but it's not 0. Okay, so that's kind of scary. But I want to tell you there are good things here. So here I want to show you a 4 by 10 ETF, and I'd like you to observe that 10 is 4 plus 1 choose 2, just like in Gerson's bound. So here's just an example in p equals 3. Here I have a non-square type quadratic form. And if this particular matrix that I cooked up in GAP using some symmetries is an ETF, the parameters are ABC is 0, 1, 0. And the way I can tell it's an ETF, so first of all, it has to be a frame. That means it spans. Its rank is 4. This is that sort of orthonormal basis-like condition. So that my frame constant here is 0. That's C is 0. And then equiangular, if I look at its Graham matrix, it looks like this. So it just has plus or minus 1s off the diagonal. So when I square that, I get 1. That's the b equals 1. And there's kind of an interesting thing here. If you look at the pattern of the minuses here in this matrix, it's the Peterson graph. So many of you are algebraic combinatorics, and maybe you look at this and you go, oh, hey, this is kind of cool. This is a way to make the Peterson graph that I didn't know about. You could see it as coming from this finite equiangular type frame. But me, I'm a harmonic analyst, so I think, this is a way to make an ETF. You start with the Peterson graph, and then you make this Seidel matrix, and then I can get this thing back. And Okay, so this is a sign that we should be friends, that we have something to offer each other. Okay, but for my thing, I want to start with the graph and get the gram matrix, and then I want to recover the frame. And I know that I can do that in real and complex space, but I'm using the spectral theorem, the way I would normally prove that or expect my students to prove that. But there is no spectral theorem. So there's a challenge here. How do I recover a frame from its gram matrix? So I want to tell you very briefly that you can, but there is an obstruction. And for the sake of time, I'm gonna move a little quickly here. So suppose that my geometry is given by this M. You see, if I have a spanning set contains a basis. And so a principal submatrix of its gram matrix is a gram matrix for the form. But then I know something about its determinant, right? That its determinant has to be in the same coset as that of M for quadratic residues. Okay, so here's what we eventually found. So you start with a G that you want to be a gram matrix, and you choose columns that form a basis for its column space. And you're thinking that this is like choosing that basis inside your spanning set. And then you look at the principal submatrix of G that corresponds to that column choice. So turns out there exists a spanning set that has G as its gram matrix if and only if these three things happen. So the first is that G has to be symmetric. The second is its rank is D. The third is that the determinant of that submatrix you picked is in the correct coset. What I want you to notice, though, I never said anything like positive semi-definite. There is no positive semi-definite kind of condition. And in fact, every symmetric matrix is a gram matrix in some orthogonal geometry. But this condition is really annoying. And so most of the time, I'm just going to say some geometry. So, okay, if I have the gram matrix, of course, I can compute the determinant and see what geometry it is. But if I'm trying to prove theorems, sometimes it's hard to predict what that determinant will be. So I'll just say some geometry. Okay, so now I can get ETFs from gram matrices. And it's like this. I have a matrix that's rank D. And this will be the gram matrix of an ABC ETF in some orthogonal geometry, if and only if these conditions hold. So the first is that it's symmetric. The second is that on the diagonal, like the norm squared, that's all going to be here, A. The second is off the diagonal, the squares are all equals to B. And then the last is that when I square it, I get some multiple of itself. So here, I just look at this gram matrix, I check those conditions, and I know there exists some ETF for which it is the gram matrix. Okay, so once I know that, you can deduce there's a lot of overlap with the real case. Yes, okay. So first of all, suppose you have a real D by N ETF and N is bigger than D plus 1. And one of these two conditions hold. So either your redundancy is not 2 and P doesn't divide this very specific, turns out that has to be an integer. So just there's finitely many divisors that you'd have to ignore. Or if N is equal to 2D and N minus 1 is a quadratic residue, then there is a D by N ETF in some orthogonal geometry on FQ to the D. So I can go from real to finite, but I can also go the other way. So if I have a D by N ETF in some orthogonal geometry, and if my characteristic P is sufficiently large, then it's sort of like when you check those conditions about the gram matrix, or really, I guess, the signature matrix, you're kind of never using your characteristic when you do those computations. You never have multiple of P to divide out because P is so big. And you can deduce that there exists a real D by N ETF. So the upshot here is that there is quite a lot of overlap with the real case, right? These two things combine to tell you these things are very similar. And I like to think that the finite field stuff is sort of an algebraic approximation of a real D by N ETF. But there's crazy stuff. There are crazy differences that I'm going to tell you some about. Okay, so there's a long history of using strong and irregular graphs to make equiangular type frames. So, and SRG, just in case you don't know, maybe for this audience, I should just shut up. But so it's a graph, simple, undirected. I'll insist that it's neither edgeless nor complete. And every vertex like this one has exactly k neighbors. So here k is 3. If I look at two adjacent vertices like these two, they have exactly lambda neighbors in common. Here, these have no neighbors in common. My lambda is 0.
And if I look at two non-adjacent vertices, like maybe these two, then they will have exactly, sorry, that's not the one, and this one. So these two have exactly one neighbor in common. So mu is equal to 1. Okay. And I'll use the following notation. So in SRG, I'll write A for its 0, 1 adjacency matrix. Maybe to many of you, that's just its adjacency matrix. Its spectrum, it have 3 things. It's got K appears with multiplicity 1, and it has 2 more eigenvalues I call R and S. R is positive, S is negative. The multiplicity of R I write is F, and of S is G. So this is, I think, standard notation. Each of these things is a function of the parameters. And then I'm going to be interested in the Seidel adjacency matrix. So it's like, maybe look down here. So here's the 0, 1 adjacency matrix. It's just I turn all those 1s into minuses, and the zeros off the diagonal become pluses, and then I keep zeros on the diagonal. So, okay, you can accomplish that by doing j minus 2a minus I, and then his spectrum is like this. This particular number is its most negative eigenvalue. So in the real case, I would want to subtract that, like add 2r plus 1, and then I'd want to have that be my Graham matrix. Okay, so this is one of our main results, is that if you have an SRG and F is not equal to G, then I make it Seidel matrix, it's plus or minus 1 adjacency, and then I subtract that like most negative eigenvalue. And then what I'm going to do, so it turns out that's an integer valued matrix. I'm going to look at it mod P. Okay, so that's what this bar means, or this I look at it mod P over FP, and D is its rank. So if P divides this specific number, then that G bar is the Graham matrix of an ETF with size D by V in some orthogonal geometry. And I can tell you stuff about D. So if R and S are different mod P, and if this number is not 0 mod P, then D has to be exactly G plus 1. If it turned out that number was 0, it'd have to be D is equal to G. And then we can say some other things. So, okay, here I have inequalities. All right, I don't want to get too much into this, but I should tell you 2 things about history. One, we certainly did not invent using SRGs to make ETFs. This is very old. I think maybe this is due to Seidel, maybe. And also we certainly didn't invent looking at SRGs mod P. This is actually used to distinguish SRGs with the same parameters up to isomorphism sometimes. But I think our contribution maybe is that the SRG corresponds to an ETF in the orthogonal geometry. Okay, there's another thing you can do, which is if you take the Seidel matrix and you pad it with all 1s, and then you add 2r plus 1. So now you have v plus 1 vectors, and often this will give you the Graham matrix of an ETF. So if P divides both of k minus 2 mu and this particular number, then this is the Graham matrix of an ETF with size D by N. And again, I can tell you some things about D. First, if R is different from S mod P, then D is definitely G plus 1. If they're equal, then I can just tell you this inequality. Okay, but the upshot here is SRGs and finite field ETFs, they want to play with each other. And maybe from your perspective, what I'm telling you is that an SRG comes from a finite field ETF unless both of these numbers here are powers of 2. And that's quite common. So Brouwer maintains a table of feasible SRG parameters, and he has, I think this is right, 211 known complementary pairs. These are known SRGs on less than or equal to 1,300 vertices. Of all of Brouwer's table, all of the green rows, all but 9 pairs come from finite field ETFs. All but 9. It's 95% of known SRGs on less than or equal to 1,300 vertices come from finite field ETFs. And here I just wrote down the 9 weirdos. So, and I don't know what's up with the 9 weirdos. But I can also get ETFs from SRGs. So here's just a bunch of data. So here, this is a characteristic, a dimension, a number of vectors, and then these are ETF parameters. My B I normalized to be 1. So all of these that appear here, there is no known real ETF with these sizes. And the ones in bold are n equals D plus 1, choose 2, like you hit Gerson's bound. So that's quite interesting. It's very different. You could also view this as necessary conditions for SRGs. So everything here is a yellow row in Brouwer's table, at least one. So maybe some of these have changed color since I last looked at this. But okay, in December, these were all yellow rows in Brouwer's table, at least according to Sage. And all of these, there's a necessary condition. There's a necessary condition that if the SRG exists, then there is a finite field ETF. And I just highlighted one. So this one right here, this is Conway's graph. So exists only if there is a 45 by 100 ETF in this in characteristic 5 with these exact parameters. And those of you who know something about ETFs, you may think, well, there's a 45 by 100 real, but when you try to do that projection move, this one falls through the cracks and you wouldn't get these parameters. So I don't know. I really don't know. It's kind of a weirdo to me. Okay, so to me, this is a problem. We'd like to have a relative bound. So the idea is you could use this to disprove SRG existence. I'd like to have, I give you an orthogonal geometry, I give you parameters A and B. I want some kind of effective upper bounds on the size of an equiangular system. And if you find me an efficient bound, this may disprove SRG existence. This is similar to what is sometimes done to prove SRGs already, thinking about real equiangular lines. So for instance, is there a 2-1 equiangular system with 100 vectors and some orthogonal geometry on F5 to the 45? If there's not, then you can prove that Conway's 99 graph does not exist. There is an absolute bound, well, not quite absolute, but there's something like Gerson's bound. And it looks like this. So if A squared is not B and you have an AB equiangular system, then N is at most D plus 1 choose 2. And if equality holds, then phi is necessarily an ETF. So this is, the proof is a little similar, similar idea, but there are more things to check. This condition A squared equals B, it avoids some trivialities like trying to take an entire isotropic subspace. That would be equiangular, but I kind of don't want to think about it in this context. Okay, and now the kind of amazing thing I want to tell you is that we hit Gerson's bound infinitely often. So for every integer D and every odd prime P that divides D minus 7, we get an ETF of D plus 1 choose 2 vectors in some D-dimensional orthogonal geometry. So Gerson's bound is saturated in some geometry as long as D minus 7 is not a power of 2. And the way we do it is with SRGs. We look at the complement of the triangular graph. So I guess this is also, I didn't know this until the other day, it's also called the Knesser graph. I don't know this. But so like the 4 by 10, it's like I'm looking, so this is sort of D plus 1 things, and I look at all 2 subsets of that, and I insist that they are adjacent when they don't overlap. So this is disjoint from that, and that's what this edge is like that. Okay. So that will give you an SRG. And if you play our game with that SRG, you hit Gerson's bound. So you have to add some identity to the Seidel matrix. You take a mod P, and you get an ETF. Sorry, I'm running low on time, so I'll just say D equals 5 is the first time where this doesn't happen, and we proved you cannot ever hit that in a finite field. So it's not that it always holds, at least not in finite fields, but a lot of the time. Okay, so I want to tell you something about unitary geometry, because we also found something pretty cool about Gerson's bound in unitary geometry. So this is going to look a lot like before. I'm trying to simulate, at least I am personally trying to simulate complex geometry. And I need something like complex conjugation. So I look on the finite field of order Q squared. So here, X maps to XQ. This is an order 2 field automorphism, much like complex conjugation. It fixes a field, it fixes the subfield FQ, much like complex conjugation fixes the reals. And so I can make a Hermitian form, which is, I would just always use this one in these slides. And it's very much like what we know and love over the complex numbers. So it's Hermitian. So when I swap, this sigma, this should be a Q. It's like its conjugate. I'm linear in the second spot. I'll be sort of anti-linear or conjugate linear in the first spot. And then I'm non-degenerate, just like before. And there's there's only one of these things up to isometric isomorphism. So that's why I just picked this one. And then I'll have all the same kind of definitions as before. But here, maybe the only interesting thing here is this, that this is like taking this number and multiplying it by its conjugate. And I'm thinking that this is like being the absolute value squared. So this is somehow telling me, I'm thinking that that's telling me about the absolute value. Okay. All these other definitions are just like before. So some examples, first of all, if you have an ETF in an orthogonal geometry, you can do some stuff with a Gram matrix and factor it and get one in a unitary geometry. But more stuff exists. So here is, when Q is 2, here is just an example of something I found by brute force search, a 6x27 ETF. And it turns out this is doubly transitive. And okay, I'll tell you something about the state of doubly transitive lines. We know now that it's not published exactly, but thanks to some work of Bill Cantor, we know now that there is no doubly transitive complex ETF of this size. It does not exist. And furthermore, there's no complex ETF of that size known at all. So there's some weird stuff here. And this plays with complex ETFs. So this is something I mentioned yesterday, a while after John Yard's talk. So first of all, if you have a D by N complex ETF, then you can do some things and you can find another one, all of whose entries are algebraic. So this turns out to be an application of Tarski-Seidenberg. And once I have something with algebraic entries, then I can play some number theory games and like mod out by great big ideals to map into finite fields. And so once I have a D by N complex ETF, then for infinitely many pairwise coprime Q, there is a D by N ETF in a unitary geometry on FQ squared to the D. I don't know about the converse of that. I'm very interested if the converse of that holds. And we have a Gerson bound. So if A squared is not B, and again, I'm trying to avoid like entire isotropic subspaces, then I can have no more than D squared vectors in an equiangular system. And if equality holds, I have to be an ETF. And there's a great big problem here. For which Q and D is Gerson's bound saturated? When do I hit that bound? So, okay, Zauner's conjecture is that it implies that for every D there exists a Q. So in some sense, this problem is strictly harder than Zauner. So it'd be harder than Zauner to solve it completely. But it's easier to make progress. And the certificate is that I'm going to hit this bound infinitely often. Okay, so I have to tell you about time frequency shifts. And this, you should think that this is like the Heisenberg group. So I want to do time frequency shifts over a finite field. So I'm only going to allow myself to play with certain abelian groups. So I'm going to make a finite abelian group like this. And so it's just a product of cyclic groups of size dk. And I want something from those dk's. And this, again, there's a typo here. So this should not be dk, but dm. Okay. I want them to all divide q plus 1. This is sort of the size of unimodular numbers. So I want to have unimodular dkth roots in my field for every k. And then I'm going to think about this space. I'll think about it as functions from my group into fq squared. Okay. And now for each k, I'm going to fix a generator I call omega k for the subgroup of size dk. And you should think that this is like a primitive dkth root of unity. And again, this condition that dk divides q plus 1, this ensures that omega k is unimodular, that when I multiply it by its conjugate, I get 1. Okay, and now I can make time frequency shifts. I can make translation and modulation operators. So I have some x, x1 to xm, and y is y1 to ym in G. And I have this function from G to fq squared. I can do a translation move. So I can translate phi by y. And the way that works is when I evaluate it at some x, I just do phi of x minus y. This is what translation should look like. I can also do a modulation move now. So I can modulate phi by y. And when I evaluate it at x, It's like phi of x multiplied by this unimodular number. Okay, so then these translation and modulation operators, these are one more typo, isometric isomorphisms. These are unitary operators. And it turns out that if you take any non-zero phi and you look at all its translations and modulations like this, that will always be a tight frame. In fact, it will be sort of a unit norm tight frame. Sometimes the frame constant will be 0, but it will still be a tight frame. In particular, it will span. Okay, and now what I really want to tell you is that we hit Gerson's bound infinitely often. So if you look specifically in characteristic 3 and your M is odd, you always choose dk as 2. So your group is Z2 crossed with itself an odd number of times. And I'm looking at like the Heisenberg group over that. This is like what John Yard was telling us about Hoger's lines. It's that kind of weirdo, looking at the Heisenberg group over this, okay? Now, you choose a primitive element in F3 squared, I call it zeta, and I'll tell you explicitly what the fiducial vector is. It's quite simple. So it's this function. At the identity, it's this number. This is -1 minus zeta squared. And everywhere else, it's 1. Wow, that's amazing. My fiducial vector is this simple. Okay, now I take that fiducial vector and I look at all its translations and modulations, and that is an ETF. It's a 0, 1, 0 ETF, and it has, in dimension 2 to the m, I have 2 to the 2m, dimension squared vectors. So Gerson's bound it's attained in a unitary geometry, characteristic 3, whenever my dimension is an odd power of 2, 2 to an odd power. So here, the tight frame part is free. So any phi, I would be a tight frame. The equiangular part, because it's so simple, you can just write it down. So I'm not going to write it down, but you can just write it down to check. And sort of our work was figuring out that, was conjuring up phi and making that happen. So there are some connections with the complex case, but they're quite limited. So I told you that Gerson's bound is attained when D is 2 to an odd power. So when D is 2 or 8, those actually lift to complex ETFs in some suitable sense. D equals 2 gives you a tetrahedron in the block sphere, like John Yard was telling us about with his beautiful pictures yesterday. D equals 8 gives you Hoger's line. So this is in some sense a projection of Hoger's lines. In some sense, what we're doing is we're extending Hoger's lines to an infinite family, but over a finite field. But D equals 32, I tried, it does not appear to lift to a complex ETF. And I don't think it should. I don't think it should, because there's a paper by Gotzel and Roy from 2009 that time frequency shifts over Z2 to the M, they can generate an ETF only if M is 1 or 3. That's sort of it. So I don't think that there is at least any kind of straightforward way to turn these finite field things into an infinite sequence and complex case. I think it's more like they want to live downstairs in the finite field, and then 2 of them are sufficiently simple that they are satisfied to live in complex space. But the others are like more sophisticated, and they won't put up with that nonsense. Something like that. Okay, here's just some more problems, and I know I'm about out of time. So there is another very nice seq that is complex Gerson equality ETF. It's a complex 3×9. Okay, there's a continuum of complex 3×9s, but there are only 2 that are doubly transitive, and they look kind of the same. So take one of those. I think that it should generalize. That should want to be something bigger over a finite field. To me, that's one of the next things to do. The next problem, I'm really interested if there's a combinatorial description of ETFs in finite unitary geometry. And I would like this because it might help me to find necessary conditions for ETFs in unitary geometry. And if I have enough conditions in finite fields, I can lift upstairs and get necessary conditions for complex ETFs. So, okay, I think I'm out of time, and I thank you for dealing with my raspy voice for this long, and I'll be happy to
to answer your questions as best I can.
Thank you, Joey. That's a nice talk. So do we have any questions? So Ferdinand has a question in the chat. He also had a comment before.
I see it now.
Okay.
Why no symplectic case? Yes. Okay. So my plan was to give it to a graduate student, but well, so that's yes, for sure. We should think about the symplectic case. I completely agree. I guess the answer is just that we haven't done it yet, but yes, I agree that we should think about that.
Yeah, I asked Gary Greaves some months ago why no symplectic case when you cover all the other polar spaces. And yeah, but now I understand graduate student is a good plan.
But you're absolutely right. It's natural to think about. And now, sorry, I see you have another comment. If there are any other finite geometries, oh, but that's not me.
I just wanted to say that for the p=3 case, what you get is, I think also in the Hermitian case or unitary case, which you mentioned later, is that you get a partial ovoid for p=3, because there your condition is equivalent of being non-orthogonal in the space. And then you get what finite geometers call a partial ovoid. And I did not want to go through the whole list of participants if there's anyone who understands what I'm saying.
But are you saying that what we have is equivalent, that you have another name for what we already call?
For a very special case, I have another name for what you call that. In general, not, because in general, it's about being orthogonal or not orthogonal, and not orthogonal in the one case is still fine, because there are not many squares or non-squares in characteristic 3. You don't have much choice. It's either 1 or 2, while in the general case, it's being orthogonal, being non-orthogonal. Of course, you can have many more numbers occurring instead of being a specific number. So then it's different. And I think in that special case, it corresponds to the normal p-rank bounds for partial ovoids, but I checked in December, so I don't remember exactly if that was the case.
Ferdinand, what exactly is a partial ovoid? Is it just a subset of an ovoid, or is it something stronger?
No, it's just a subset. It's just a co-clique. Yeah. So you could also just say it's a co-clique in the non-collinearity graph.
Yeah, okay, thanks. This is a vague comment, but the MUBs, there's a paper by Cantor and others, I think Bill might be looking here, where they pass backwards and forwards between the complex geometry and geometry over Z2.
I see. Are you thinking about real MUBs? This
No,
is okay.
This is the big paper, is it?
Yeah, Cantor, Calderbank, Seidel, and might be Cameron, I'm not sure. But
yeah, so that was, yeah.
There's a beautiful sort of master diagram of the mapping between characteristic 0 and positive characteristic.
I see. Okay.
Yeah, you'll find it pretty quickly if you Google. And if you have any trouble, let me know.
Okay, thank you. Yeah, I'll look into that.
I'd like to ask if there's anything qualitatively different about the case when the frame constant is 0.
Good question. When the frame constant is 0. So yes, there is something different. And something different happens, especially when you hit Gerson's bound. So let's see. Yeah, so you may have noticed I was very careful. I didn't call this a seek. And when I do these phi stars, if you just indulge me in what phi star means, but its trace here has to be 0. So the outer products have to have trace 0, and they cannot span the entire space. The best they can do is span the subspace of trace 0 operators.
And oh, I'm sorry, that's sort of A equals 0. I'm sorry. But it's kind of related. And yes, I'm sorry, I'm getting tired. My cold is getting the better of me.
No
So
worries.
this is A equals 0, what I'm saying. It's not the question you asked. But something different about C equals 0 when the frame constant is 0. Yeah, it is a little bit different. Yes, it is for sure different. So one thing is that the Graham matrix now, when it squares, it's 0. So Graham matrix is nilpotent, and that's kind of different. And like that feels wrong to me, that a Graham matrix should be nilpotent, just because I'm used to thinking about the real and complex case. So that's kind of weird. And also C equals 0 is, you could think about it like this way, that I do my what's called the analysis operator. So the analysis operator is going to map, well, it's going to map my geometry. So here, I'll just think like this, into like this, and it's sort of, it's giving me this sequence. It's the measurement operator, like that. And this thing, so C equals 0 happens, frame constant 0. This implies that the image of phi star is totally isotropic. So in terms of geometry, it's kind of a different animal. It's, and in fact, so this is sort of equivalent if you also insist that you're a frame, that your vectors span. So okay, I don't know if I've really answered your question, but I have told you some different things that happen when.
Yeah, I mean, it was a sort of vague question to begin with.
Yes.
But yeah, I was just looking at, your two tables on slides 27 and 28, and, seeing a lot of zeros from when you get an ETF from an SRG, and then none when you have these necessary conditions. And I was wondering.
Yeah, I see. Okay. So there are kind of two things going on there. So one is that I had limited amount of space to put things, and so a lot of them were when Q or P was equal to 3. When P was equal to 3, there are only 3 things it could possibly be. So it's kind of higher probability that it's 0. But the other thing I think that's happening is in that table, and maybe I'll show it again, so we don't look at it together. No, these are necessary. This one. So in this table, I only wrote down sizes that don't exist over the reals. So so they're somehow taking advantage of something that's different in the finite geometry. And to me, one of the main things that is different in the finite geometry is the existence of isotropy. So in that sense, it's maybe not surprising that A equals 0 and C equals 0 should show up. That's one of the main features to try to leverage for something.
Right.
That's a good question. Thank you.
Can I ask another question?
Yes, please.
For all the tables of ETFs, I think I forgot to ask that when I asked Gary a month ago. Did you investigate, like, if some of your examples you find are very symmetric, for instance? So if there is a large subgroup of the orthogonal group acting on them, or?
Yeah. I really like that question. Some of them we did. So, and I had to go kind of quickly at this point, but I mentioned this one right here. So this one is one of a few that I found through kind of a brute force search in GAP. And what I was doing, the way I found this actually was, in my mind, I was kind of using Witt's extension theorem a couple times, and I knew that I could ensure that the first vector was this one and the second one was that one. And then I was looking at the graph of all things that had angle, all isotropic vectors that had angle 1 with both of these guys. And then, so that's some graph. And then I said, Gap, I'd like you to find me a large clique inside that graph. And so that's some big equiangular system. And then I checked and it was tight. And then I asked myself the question you just asked, which is, what is its isometry group? And this particular one it has a doubly transitive automorphism group. So that's kind of surprising. So I have another project with Dustin Mixon. We're trying to classify all of the complex doubly transitive lines. And there just aren't very many of them. And so this size doesn't happen. So, okay, here's one example of a weirdo with a big automorphism group. But in general, yeah, this is something I'm quite interested in. Okay, one more thing is we did not, and I should have said this is a problem, we did not compute the automorphism group of this thing. So I mentioned that when d equals 2 or 8, it kind of is the same thing, or you can lift it to a complex case. Well, that complex 2×4 and that complex 8×64, those again are doubly transitive. I don't know if these have a great big automorphism group or not, but I kind of think that they do. And then sort of a third thing is, yeah, I'm really interested in trying to use groups to make more examples, but it's more challenging for sure because the representation theory we'd have to play with is modular representation theory, which is kind of a hairier animal to try to play with. And moreover, I would want to impose another condition. Like, I don't just want a modular representation, I want it to be unitary or in the orthogonal group, which is a stronger condition. And trying to play games with that, well, I don't know. I'm not an expert in that area, and it seems to be kind of a challenge. But I am quite interested in that direction.
I mean, one of the reasons I was asking is sometimes you find constructions in finite geometry by first you find an example, one small example, then you find a second small example with a large group. You notice that the two groups usually don't have much more than 2 examples, that they might belong to a common family of more groups. And then you make a good guess which group to impose. And then you figure it out that it works for that in general. Now I was wondering, you never tried intentionally to just prescribe a group that has to act on the thing, and then like you could just go for all relatively large subgroups and check. I mean, then you can usually reduce things, reduce a lot computationally, but then your dimensions and get very large. So I don't know how feasible that is.
And that's a good idea. That's a good idea. And actually, the specific 4×10 that I showed here, that's actually how I found this specific 4×10. So I knew that it existed, but to get the short fat matrix, for me, the fastest thing, where'd it go? What I actually did in practice to figure out what this matrix was is in GAP, I went, this thing has got a bunch of symmetries. So I looked in the orthogonal group and I was just asking for relatively large subgroups. And I was just looking at their orbits on the isotropic vectors because I knew that this one I knew was supposed to be isotropic. And I was just asking, and then I would check, is this orbit a tight frame? So that was how I in practice factored this grand matrix. But that could be kind of a discovery tool. That's a good idea. So one could just kind of look at small dimension, small characteristic in GAP, and just look at just like I was doing here, look at subgroups, and then maybe I insisted acts on isotropic vectors or something like that, and check out orbits and see if one of them is a tight frame, is an equiangular type.
Yes, that is what finite geometers do all the time for finding objects to which they give strange names, but usually there's just things like cliques or co-cliques.
Yeah, that's kind of what this is. That's a good idea. Thank you.